In this lecture, we're going to talk about Chapter 6, Types of Chemical Reactions and Solution Stoichiometry. We'll cover the unique properties of water, and we'll relate those properties to the molecular geometry of water. We're then going to write chemical reactions for the dissolution of ionic compounds in water. We'll look at the strong, weak, and non-electrolyte solutions. We'll talk about acids and bases, and we're definitely going to point out the 6 strong acids that you need to know. We'll then look at some calculations that involve solution stoichiometry. We'll determine the concentration or amount of solute in solution. We'll move on to precipitation reactions. We'll use the solubility rules to predict whether or not a precipitate will form. We'll look at acid-base reactions. We'll use the solubility rules and the knowledge of acid-base behavior to predict the products of these reactions. We'll talk about oxidation reduction reactions, and we'll balance very simple reactions. And we'll perform stoichiometry calculations for precipitation reactions, as well as acid-base reactions. So we have a lot to cover in this chapter. Let's get started. I want to start with water. Okay, so we already know how to draw Lewis structures, and if we were to draw the Lewis structure of water, we would first start with the formula H2O or HOH, and we would count up the valence electrons. There's 8 valence electrons in water. And so we would start with the skeletal structure. We would then complete the octet for oxygen, which would put 2 lone pairs on oxygen, and that would essentially use up all of the valence electrons. So there is your Lewis structure for water. Of course, with there being 2 bonds and 2 lone pairs, we know that it has a bent geometry. And the bent geometry is what makes water polar instead of being nonpolar. So with water being polar, ionic compounds are going to dissolve very well in water because an ionic compound contains a cation, a positive ion, and an anion, a negative ion. And so because of the polarity of water, the negative side of water is going to dissolve the positive cation. The positive side of water will be attracted to the negative side of water. Okay, so when salts dissolve in water, because they have positive and negative charges, they are going to split up into those ions. So if you're asked to write the equation representing the dissolution of any salt, like ammonium sulfate, you should be able to do that. You start with the formula for ammonium sulfate, and it's there. And then you would break it up into its constituent ions, the ammonium ion, NH4+, and the sulfate ion, SO4 2-. In the formula, since there are 2 ammonium ions, you'll have 2 ammonium ions on the product side of the reaction. Make sure that you are able to write those types of reactions. Now, if we were to take a conductivity apparatus and use it with a soluble salt, we would find that there would be conductivity, and we would see the light bulb burning very brightly in the presence of a soluble salt. We can look at a series of different samples and predict whether or not the bulb would burn brightly, dimly, or not at all. We'll start with tap water. If we were to use that apparatus with tap water, we would find that the bulb would burn dimly. And the bulb would burn dimly because water is a substance that contains impurities, and those impurities are ions, and they would cause the bulb to burn brightly. Distilled water, on the other hand, being pure water, you would see no light whatsoever, and the distilled water would essentially, because it's a molecular compound, you would see that it would have no light whatsoever. The sodium chloride, on the other hand, when you dissolve it in water, the bulb would burn brightly because sodium chloride dissociates to sodium ions and chloride ions. Same thing with hydrochloric acid. It would dissociate to form hydronium ions and chloride ions. You'd have lots of ions moving in solution. You would expect a bright light. Sodium hydroxide, NaOH. Sodium hydroxide is a strong base. It would break up into its constituent ions. There would be a lot of ions present, and so you'd have a bright light. What about C6H12O6? This is glucose, okay? This is a molecular compound. It's not ionic. When it dissolves in water, yes, it hydrogen bonds with water, but it does not form positive and negative ions. Therefore, any molecular compound that dissolves in water would produce no light. It would be a non-electrolyte because there are no ions being formed. What about acetic acid, HC2H3O2? This is not one of your 6 strong acids, therefore it's a weak acid. Weak acids only dissociate partially. It will produce a few ions. If it produces a few ions, you would expect it to have a dim light, and therefore acetic acid would be a weak electrolyte. The types of solutions that are strong electrolytes are soluble salts, as we saw on the previous slide, strong acids, as well as strong bases. Hydrochloric acid, HCl, a strong acid. Sodium hydroxide, NaOH, a strong base. Both of those are strong electrolytes. What types of samples are non-electrolytes? Those would be your molecular compounds, as well as your insoluble salts. The compounds that would form weak electrolytes, as we saw, were the weak acids like acetic acid, HC2H3O2, as well as the weak bases. Okay, so an acid is a substance that when you dissolve it in water, it produces hydronium or H3O plus ions. That is the Arrhenius definition of an acid. We have 6 strong acids, and they need to be memorized. They are HCl, hydrochloric acid, HBr, hydrobromic acid, HI, hydroiodic acid, and then we have 3 that have polyatomic ions, and they are nitric acid, HNO3, perchloric acid, HClO4, and sulfuric acid, H2SO4. All of these acids are strong acids. Any other acid that is not one of these 6 strong acids, we would automatically assume it to be weak. So the way we do that is we know our 6 strong acids. Any other acid is a weak acid. If we want to dissolve an acid like hydrobromic acid in water, here's what would happen. You'd have HBr plus H2O, and they would react to form hydronium ions, because remember the definition of a strong acid, they produce hydronium ions. So they would react to form H3O plus and Br minus. What if we had something like acetic acid? Well, first of all, acetic acid comes from the acetate ion. You already know that ion, C2H3O2 minus. Combine it with H plus and you get HC2H3O2. Add it to water and they react to form H3O plus, hydronium ions, and C2H3O2 minus, acetate ions. This will be a common theme when we are dissolving an acid in water. This is how the equation will be set up. Since acetic acid is weak acid, it will partially dissociate, and therefore we use equilibrium arrows. Now, a base, on the other hand, is a substance that produces hydroxide, OH minus ions, when we dissolve it in water. We have 6 standard strong bases, and they are, if you look at the periodic table and look at the alkali group 1 metals, you have lithium, sodium, potassium. Those 3 hydroxides are the first 3 of our 6 strong bases. Now, next to potassium, go to the alkaline earth metals, you have calcium, calcium hydroxide. Below calcium, we have strontium, so strontium hydroxide. And finally, barium hydroxide. So on the periodic table, it kind of forms an L shape, and those will be your 6 strong bases. When you take a strong base and you dissolve it in water, it will dissociate to form the cation and the anion. So for example, lithium hydroxide, dissolve it in water, it's going to form lithium ions and hydroxide ions. What if we needed the dissolution reaction for a weak base like ammonia? Well, we know the formula for ammonia. It is NH3. When you combine NH3 with water, there will be an exchange of protons. The NH3 will accept a proton from water. Water will turn into hydroxide ions, and the equation will look like this. So weak bases will combine with water. They will accept a proton, H plus, from water, and in the case of NH3, it becomes NH4 plus, the conjugate acid of NH3. And then water, after it is given an H plus to NH3, it becomes OH minus. So that is the standard format for the dissolution reaction for a weak base such as ammonia. Now we use equilibrium arrows for weak acids and weak bases, and the equilibrium arrows show a partial dissociation, not a full dissociation. All right, so now that we've understand what a strong and a weak acid are and what your strong electrolytes are, your weak electrolytes and your non-electrolytes, now we're getting into the mathematics of solutions. We need to be able to express solution concentration in various units. The first one we're going to talk about is molarity. Molarity is defined as the moles of solute per liter of solution. So capital M is the designation for molarity. When you see a capital M, that means molarity or molar, and the molarity is the moles of solute per liter of solution. We'll look at some problems where we need to do calculations around molarity. We'll start with a very simple one. We have a solution that has a molarity of 0.209 moles per liter. Again, when you see that capital M, it means moles per liter of cobalt to bromide. So the cobalt, Roman numeral 2, means cobalt has a +2 or +2 charge. We need to be able to write the formula, obviously, to do this problem. Now, since the molarity is telling me that we have 0.209 moles in 1 liter, we can then figure out, well, how many moles would be present in 0.3 liters? So we will plug in the 0.209 molar into the molarity, leave moles of solute as the unknown variable, and put the volume as 0.3 liters rather than 1 liter. Rearrange, solve for moles of solute, and we get 0.0627 moles in 0.300 liters of solution. So we can use the molarity equation to calculate any one of those variables. We can use it to calculate molarity, but if we have molarity in liters, we can use it to calculate moles of solute. Another problem you might see, OWL 6.2, in the laboratory you dissolve 20.9 grams of cobalt 2 bromide in a volumetric flask, and you add water to a total volume of 375 milliliters. Of course, we know that is 0.375 liters. What's the molarity of the solution? Well, we need moles of solute. We don't have moles, we have grams. So we're going to convert those grams to moles. In order to convert to moles, we need the molar mass of the salt. In this case, it is 218.73 grams in 1 mole. So let's use the grams we were given and calculate moles. When we do that, it turns out that we have 0.09555 moles of solute. We'll take the moles of solute and dissolve it and divide it by the liters of solution, 0.375 liters. And when we divide those two numbers out, we get 0.255 moles per liter of cobalt 2 bromide. What if we're asked for the concentration of the individual ions in the salt? Well, the formula for the salt was COBr2. Now, if we want the concentration of cobalt-2 ions, well, there's only one cobalt-2 ion in the formula for the salt, so it would be the same. It would still be 0.255 moles per liter of cobalt-2 ions. On the other hand, if we want the concentration of bromide ions, there are 2 bromides for every 1 cobalt-2 bromide. Therefore, as you can see in the calculation, we multiply the molarity by 2 and we get 0.510 moles per liter of bromide ions. So you could be asked for the molarity of the salt, and that's the first thing that we calculated, or you could be asked for the molarity of one of the ions in the salt. If there's one ion like cobalt-2 ion, then the molarity of the ion is the same as the salt. On the other hand, if there's 2 of the ion like the bromides, you can see the molarity of the bromide is twice that of the molarity of the salt. Now, sometimes in chemistry, we have to do a dilution calculation. And by the way, if you need extra help with any of these topics, I have videos that are linked within the main video. Dilution is the process of adding water to a solution to decrease its initial concentration. The equation that we use for dilutions is MCVC, that is the molarity of the concentrated solution times the volume of the concentrated solution, is equal to MDVD, the molarity of the diluted solution times the volume of the diluted solution. OWL 6.3. In the laboratory, a student dilutes 14.7 milliliters of 11.3 molar hydrochloric acid. The total volume after dilution ends up being 250 milliliters. We want to calculate the concentration of the diluted solution. I recommend first you summarize the data that you're given. We know that the molarity of the concentrated solution is 14.7. We know that the volume is 11.3, and we want to calculate the molarity of the dilute solution. We have the volume of the dilute solution to be 250.0 milliliters. We plug all of that in. We calculate the molarity of the diluted solution to be 0.664 moles per liter. Very simple way of doing a dilution calculation. We're going to look at some chemical reactions, and we're going to do solution stoichiometry on those reactions. We'll start with precipitation. Precipitation is when 2 ionic compounds react, forming an insoluble solid product. Then we have acid-base neutralization. This is where you have an acid and base reacting together to form a salt, and the second product is usually water. The third type of reaction is oxidation reduction or redox reaction. This is where we have a reducing agent transferring electrons to an oxidizing agent. So instead of transferring a proton like we see in an acid-base reaction, we're transferring an electron. Let's start with the precipitation reactions. What is a precipitate? A precipitate is when an insoluble solid forms in solution. We can see on the picture on the right, we had a clear colorless solution in the beaker. We had a clear yellow solution in the graduated cylinder. But when we combine them together, what happened? A yellow solid formed. So that's a precipitation reaction. We're forming an insoluble solid. Now, if we were to react lead 2 nitrate with potassium iodide, we should be able to predict the products. The way we're going to do that is switch partners. So lead 2 nitrate, Pb plus 2, NO3 minus 1. We end up needing 2 nitrates to finish that formula. Potassium iodide, K plus 1, I minus 1, equal and opposite charges. The formula is just Ki. The products, we switch partners. The lead goes with the iodide, the potassium goes with the nitrate. So the first product is PbI, but we need 2 I's because the lead has a positive 2 charge. Now, when we look up the solubility of that, it's going to follow the solubility of chlorides. And we know that the group 17 salts are all soluble with the exception of PMS, lead, mercury, and silver. Lead is an insoluble exception. So while most iodides are soluble, lead 2 iodide is insoluble. And an insoluble solid, that is our precipitate. So there it is, lead 2 iodide, a solid, an insoluble solid. The other product formed from potassium combining with NO3 nitrate is a soluble solid. Now, the equation is not balanced. In order to balance it, we'll need 2 KNO3s, 2 KIs, and 1 lead 2 nitrate, 1 lead 2 iodide. Now we have a complete balanced equation. To figure out whether or not your product is going to precipitate, you need to understand the solubility rules. We'll start with the soluble ionic compounds. It turns out all lithium, sodium, potassium, that's your group 1 cations, in addition to ammonium, all of those are soluble. What about the anions? Well, nitrates are always soluble. Acetates, which are sometimes written C2H3O2-, or as you see here, CH3CO2-, they are always soluble. Chlorate, ClO3-, and perchlorate, they're also always soluble. The next group that are soluble are the group 17 salts, chlorides, bromides, and iodides. Almost always soluble, but we do have the exceptions of lead 2, silver 1, and mercury 1. Those particular combinations with chloride, bromide, iodide will be insoluble solids. Otherwise, like I said, all chlorides, bromides, and iodides are soluble. We move on to the sulfates, group 3. All sulfates are soluble. The exceptions are the same as with the group 17, the lead, silver, and mercury, as well as calcium, strontium, and barium. Sulfates are also insoluble. Other than those 6, when you combine sulfate with any cation, you'll get a soluble salt. We have some salts that are not soluble most of the time. The first group are the hydroxides, OH-. Almost all hydroxides are insoluble. The soluble exceptions are group 1, lithium, sodium, potassium, ammonium, NH4+, because it behaves like those, and then calcium, strontium, barium. In this case, those are the soluble exceptions. Otherwise, all hydroxides are not soluble. The others that are not soluble are sulfides, S2-, oxides, O2-, carbonates, CO3-2-, and phosphates, PO4-3-. Those are typically insoluble. The only soluble exceptions are lithium, sodium, potassium, as well as ammonium. Now, you might be thinking, how in the world am I going to remember this? Well, we have an easy memory tool. Check out this 2.5-minute video to see how it works. I'm going to summarize it for you briefly right here. It's called NAG-SAG. The soluble salts are the NAG-SAGs. What are they? NAG are the nitrates. A are the acetates. G, group 1, lithium, sodium, potassium. What about S, sulfates? Notice we have some exceptions. Moving on to A, ammonium. The ammonium salts are soluble. And finally, the group 17 are soluble, but we have an asterisk for some insoluble exceptions. The insoluble exceptions with the sulfates and the group 17 nonmetals are as follows: PMS, lead, mercury, silver, and then Castrobare, calcium, strontium, barium. So for the sulfates, all of those are insoluble exceptions. For the group 17 nonmetal ions, only the lead, mercury, and silver are the insoluble exceptions. Otherwise, all group 17 anion salts are soluble. So NAG-SAG is a great memory tool to remember the things that are always or almost always soluble. Let's look at a few examples, and you'll have a chance to practice this with OWL 6.4, sodium carbonate. Okay, Is it a soluble or insoluble salt? Well, sodium carbonate is a sodium salt, and we know that sodium salts are always soluble. Therefore, anything I combine with sodium will be soluble. What about electrolyte? Well, one of the things that would always be a strong electrolyte was the soluble salt. So sodium carbonate, being a soluble salt, will form a strong electrolyte. Moving on to lead 2 chloride. Practice your formula writing skills. Lead 2 means Pb with a +2 charge. Chloride is Cl-. To get the formula right, we need Pb with Cl2. Okay, to figure out whether it's soluble or insoluble, we need to look at the rules. Chloride is a group 17 anion, and they are always soluble with the exception of PMS, lead, mercury, and silver. And there we have an insoluble exception with lead. Therefore, lead 2 chloride is insoluble. Now that we know it's insoluble, we look at its electrolyte behavior, and we learned that insoluble salts are non-electrolytes. Does that make sense? Let's go to the next one. Aluminum sulfate. We don't have any rules with aluminum, but we do have a rule with sulfates. That was one of our NAG/SAG salts. Sulfates are always soluble. There are a few insoluble exceptions, and they are PMS, lead, mercury, silver, Castrobare, calcium, strontium, barium. Aluminum is not one of those insoluble exceptions. Therefore, aluminum sulfate is soluble. Knowing that it's soluble, we can then say, okay, a soluble salt will always form a strong electrolyte. So you have to get the formula, you have to apply your solubility rules. Depending on the solubility, you will figure out if it's a strong, non, or weak electrolyte. Ammonium oxide, NH4, taken twice, O. Okay, all ammonium salts are soluble. Since it's a soluble salt, it's a strong electrolyte. Magnesium hydroxide. So we had the Castrobare exceptions. Magnesium is not one of those. Therefore, this is still an insoluble salt. Since it's an insoluble salt, we would expect it to be a non-electrolyte. When we look at reactions, like we were talking about earlier, the precipitation, the acid-base, the redox reactions, we have 3 different ways of expressing these reactions. We have the formula equation. This is the balanced equation with all correct formulas, including states of matters, and we would balance that equation. Next, we have the complete or total ionic equation. This is where we would take our soluble ionics and our strong acids and base, split them into ions. However, our insoluble salts would remain molecular. And then the net ionic equation, we're going to cancel out any spectator ions that are the same on both sides of the equation, and what we are left with is the net ionic equation. So let's look at an example. We need the complete ionic, the net ionic reactions for potassium carbonate with barium nitrate. So formula writing is critical. You have to be able to apply charges to figure out subscripts and write accurate formulas. As you can see, they're not all 1-to-1. We have K2CO3, we have BaNO3 and then we're forming KNO3 and BaCO3. We need to be able to balance that equation. In order to do so, we're going to have a 2 in front of the KNO3 and a 1 in front of everything else. Once we've done that, we have the formula equation. The next equation is the complete ionic. The complete ionic equation is where you split soluble, aqueous soluble compounds into their constituent ions, making sure any subscripts become coefficients for individual ions like potassium. Of course, carbonate is a group. It behaves as a unit. We're not going to separate the carbon from the oxygen. We will put the charge of carbonate, which is -2. Both of those are aqueous soluble ions. Moving on to the barium nitrate. That's another soluble salt, so it forms barium ions and 2 nitrate ions. These soluble ions react to form potassium nitrate, a soluble salt. All soluble salts get split into their constituent ions, The second product is barium carbonate. Looking at our solubility rules, all carbonates are insoluble except sodium, lithium, potassium. Barium, though, is not one of those soluble exceptions. Therefore, barium carbonate is insoluble, and it will remain together in the complete ionic equation. What do I do next? For the net ionic equation, I'm going to cancel out any spectator ions. That means I'll cancel out the potassium ions and I'll cancel out the nitrate ions. What am I left with? I'm left with carbonate ion reacting with barium ion to form the insoluble barium carbonate salt. And there you have it, the net ionic equation. You should be able to do something similar with OWL 6.5. However, notice they only asked for the net ionic equation. What I tell students to do is start with the product then. Silver sulfide is the precipitate, so that is your product. Write the formula for silver sulfide. Well, silver is +1, sulfide is -2. So the formula will be Ag2S. And that is our precipitate, our insoluble product. So we give it a solid state of matter. Then we write out the formulas for the reactants. Well, silver sulfide is formed from 2 silver ions combining with 1 sulfide ion. So we put that together and we end up with our net ionic equation. As you can see, it's a much simpler process than what we saw on the previous slide where we had to write the formula equation, complete ionic equation, and the net ionic. Here we only want the net ionic. So which do you need to know how to do? You need to know how to do both. Number 6, does a reaction occur when aqueous solutions of ammonium carbonate and sodium bromide are combined? Well, we're going to switch partners and see if either of the products are insoluble. I'm going to combine ammonium with bromide. That will still be soluble because all ammonium salts are soluble. Combine sodium with carbonate. Will it form a precipitate? No, sodium carbonate is a soluble salt. So if both products are soluble, will there be a reaction? No, there will not be a reaction. Therefore, there's no reaction, there's no net ionic equation to write. Let's look at another situation. Now we're combining solutions of ammonium carbonate with magnesium bromide. Switch partners to see if either product is insoluble. Ammonium bromide is the first product. Will ammonium bromide be a precipitate? Well, all ammonium salts are soluble. Therefore, I can put ammonium with anything. It's not going to precipitate. It will not be an insoluble solid. Let's look at the other combination. Magnesium with carbonate. So the rule with carbonates was they're all insoluble except group 1A and ammonium. Is magnesium group 1A? No, it is not. Therefore, when magnesium combines with carbonate, it will form an insoluble precipitate. So does a reaction occur? Absolutely. So we need to write the equation now for the combination of magnesium ions with carbonate ions to form magnesium carbonate. And magnesium carbonate is MgCO3 solid. On the reactant side, you'll have Mg2 plus aqueous adding or reacting with CO3 2- aqueous, and they will react to form MgCO3, the insoluble solid product. Let's do some stoichiometry. So we now understand what a precipitation reaction is. Let's apply the stoichiometry that we've already learned to these types of reactions. You're given a problem where you have 2 salts reacting to form an insoluble product. We need a balanced equation, which we have here. We need to then calculate the grams of the product that will form when so many mils of one solution are reacted. So as you can see here, we're going to set up the stoichiometry. Volume times molarity gives you moles. Moles of the reactant times the mole ratio of product to reactant gives you the moles of product. And then finally, we will use a molar mass, which we calculate on our own of the product to figure out the grams of product. And in this problem, we end up with 6.06 grams of Ag2CO3. If you need more help with solution stoichiometry, please check out the YouTube video that I have linked above. We're going to look at acid-base reactions. An acid is a proton or H+ donor in Bronsted-Lowry theory. A base is a proton acceptor. That's different than the Arrhenius definitions, which are an acid is a hydronium producer and a base is a hydroxide producer. With the Bronsted-Lowry definition, we're passing a proton, H+, from the acid to the base. If the reaction involves a strong acid or base, the acid or base is ionized. However, if the reaction involves a weak acid or base, the acid or base is not ionized because the majority remains molecular or together. So the first thing you need to be able to do is write a net ionic equation for the reaction between aqueous solutions of acid and base. Now, we'll go ahead and take the acid, combine it with the base, and form the product, which is water. So this is the net ionic equation. That is always going to be the case when you have a strong acid and a strong base reacting together. It's just going to be H+ plus OH minus yields H2O. What if we had a weak acid reacting with a strong base? Hydrocyanic acid is not a strong acid, therefore it's weak. A weak acid will remain molecular. However, the strong base will only have its hydroxide reacting, and when these two combine, you get H2O and Cn-. There's your net ionic equation of a weak acid reacting with a strong base. Here we have a weak base reacting with a weak acid. So both are weak now. So we'll take our weak acid, our weak base, we'll combine them together. We get a salt, and that is where it ends, is right there. So we cannot eliminate any of the ions because we have a weak acid and a weak base, and there are no spectator ions in the reaction. What we would conclude is that for all strong acid, strong base reactions, the net ionic equation is very simple. H+ plus OH minus yields H2O liquid. When we do a titration, we're using this laboratory technique to figure out what the concentration of our unknown solution is. And we do this by adding small amounts of reactant until a stoichiometric amount has been added, and we see the color change that we're looking for. In the case here, we're looking for a very pale pink change that occurs when you have phenolphthalein as your indicator. All right, so there are calculations associated with every titration. For example, you might be given the molarity of the titrant, but you don't know the molarity of the acid that's in solution. You know the volume that it took to get there, so we can set up a stoichiometry calculation. As you know, with stoichiometry, you always need a balanced equation before you can do the stoichiometry. For this reaction, everything is a 1-to-1 ratio. We set up the stoichiometry. We have the volume and the molarity of the one reactant. We multiply those together. Then we multiply it by the coefficient ratio to get the moles of the other reactant. And then we divide it by the volume that it took to get to the endpoint. And that's going to give us the molarity of the reactant. Sometimes, though, we need to calculate the percent, not the molarity. So we're given grams of a sample, and we use the titration to figure out the moles and the grams of the acid or base. So in this case, we will use that calculation to figure out the grams of acid, in this case, HNO3. Once you have the grams of acid, you can divide it by the grams of sample, multiply it by 100, and get the percent of the acid in the sample. In this case, it turns out to be 29.4%. So we use the stoichiometry to figure out the grams of the acid, but then we took the grams of the acid and divided it by the grams of the sample, multiply by 100 to get the percent of the acid in the sample. Check out the video linked above to get more help with these types of problems. The last thing that we want to talk about are oxidation reduction or redox reactions. This is where one reactant donates electrons and the other reactant accepts electrons. This causes the oxidation states to change. What is oxidation state? Oxidation state is kind of like the charge, but for molecular species, there's no charge, and so we need ways of calculating oxidation number. We have certain rules that are going to help us with that. First of all, an atom in an element, its oxidation number is always 0. Some examples are sodium, oxygen, ozone, and mercury. If I have charged species, the charge on the species is going to be the oxidation number of those species. If I have a sodium ion, the oxidation number is +1. Chloride ion, oxidation number, -1. Fluoride almost always has an oxidation number of -1. Oxygen almost always has an oxidation number of -2, even in water or carbon dioxide. And hydrogen almost always has an oxidation number of +1. So using these rules of thumb, we can then figure out the oxidation numbers of other elements in our compounds. Let's try a few examples. Carbon dioxide, we know oxygen almost always has an oxidation number of -2, and there are 2 of them in the formula. Therefore, 2 times -2 is -4. What is the oxidation number of carbon? Well, this is a neutral molecule. They have to add to 0. That means carbon's oxidation number is +2, since the 2 oxygens together are -4. What about SF6? Well, fluorine is always -1, and there are 6 of them. 6 times -1 is -6, therefore sulfur must be +6. What about the nitrate ion? This one has a residual charge. Oxygen being always -2 and the residual charge being -1 means nitrogen has to have an oxidation number of +5. Oxidation is the loss of electrons. Reduction is the gain of electrons. In a redox reaction, the species oxidized loses electrons and its oxidation number increases. The species reduced gains electrons and its oxidation number decreases. The agents, the oxidizing agent and reducing agents, are the opposite of the species undergoing oxidation and reduction. So the oxidizing agent gets reduced. The reducing agent gets oxidized. So I think of it as opposites when I'm talking about these types of reactions. Let's look at an example. We have metallic copper solid, reacting with silver ions. And when they react, they are exchanging electrons, because look what happens. The copper metal loses an electron and becomes copper +1. The silver ion gains that E-, that electron, and becomes silver metal. So we've transferred an electron from the copper to the silver. The species that lost electrons is the species oxidized, and that would be the copper solid. The species that gained electrons is the species reduced, that would be the silver ions. To figure out the oxidizing agent and the reducing agent, you're just going to flip-flop them around. The species reduced becomes the oxidizing agent, the species oxidized becomes the reducing agent. Notice we didn't look at the products, we only looked at the reactants in terms of defining the species oxidized, species reduced, oxidizing agent, and reducing agent. All of these things are all reactants, they are not products. Now, how do we balance a redox reaction? We're going to follow this process. First, write the unbalanced reaction. Second, determine the oxidation states of all atoms in the reactants and products. Third, show the electrons gained and lost using tie lines. Fourth, use coefficients to equalize those electrons gained and lost. 5, balance the rest of the equation by inspection. 6, add appropriate states. Let's look at an example, OWL 6.14. We have tin 2 ions reacting with copper 1 ions. We're forming tin metal and copper 2 ions. We have tie lines already shown here. What is tin doing? It's going from +2 to 0. Is it gaining or losing electrons? It's gaining 2 electrons. Therefore, tin-2 is being reduced. Let's look at what's happening with copper-1. Copper-1 is changing into copper-2. It's becoming more positive. It is losing electrons. Copper-1 is being oxidized. We have a gain of 2 electrons by tin, but a loss of only 1 electron by copper. So the electrons are not equal. That's when we need to double the copper. Now the electrons are equal. And so water will not appear. There are 2 electrons transferred. The species oxidized is the copper-1 ion. The species reduced is the tin-2 ion. So that is an example of a redox equation that you need to balance and then answer questions. For this next one, I will tell you OWL 6.15 is a bonus type of problem on the test. These are a little bit more challenging. There's a few more steps involved. But as you can see, we start with the tie lines. We notice nitrogen is changing, and so is antimony. Nitrogen is a positive 2 on the left side of the equation, and on the right side of the equation, it's positive 5, excuse me. Nitrogen is getting more positive. It's being oxidized. Getting more positive is oxidation. How many electrons did it lose? Well, it went from +2 to +5. That's 3 electrons. Now, let's look at antimony, excuse me. Antimony, first of all, we do need to double on the right because we have 2 antimonies on the left. So the antimonies are going from +5 to +3, and that is definitely reduction. And so we now are going to figure out what's happening in order to balance the rest of the reaction. So we equalize the electrons first by multiplying the compounds by 4 and the antimony compounds by 3. Then we balance the oxygen by adding water to the side that needs oxygen, and that's the right side. Now we add hydrogen ions to the side that needs H+ ions, and that would be the left side. So we now have an equation that is balanced in terms of atoms and in terms of residual charge. We just need to answer the questions. Water appears as a product. It has a coefficient of 1. Electrons transferred. Well, we had 3 electrons transferred, but we had to multiply the nitrogens by 4 and the antimonies by 3 and 6. So that means there's a total of 12 electrons transferred. What about oxidizing agent? The oxidizing agent is the species reduced, which would be Sb2O5. The reducing agent is the species oxidized, which would be NO. So like I said, you will need to try this in OWL, but in terms of the test, this type of question will be a bonus question. That concludes Chapter 6. As always, feel free to let me know if you have any questions. Don't hesitate to reach out. Thank you so much.